All right, guys, so you chose this specific guided notes because you want a little bit extra instruction on this, and I totally understand. Actually, I would encourage you to do the guided notes because I think this is a hard objective, and just writing down the notes, I don't think for most people will be helpful. Maybe it will be, but don't be discouraged. This is a little bit longer of a video, but it's going to take you through all the notes and hopefully increase your understanding than just copying the notes down. Before you do that, make sure you have both note sheets. There's an endothermic, which increases temperature, and an exothermic. You will see both of those back where you see the notes. There's two different stacks. So let me know if you have any questions, but definitely get those because that'll save you some time. So what we're going to do is we're going to go through objective 3.1, which is temperature versus time graphs and phase changes. Now, we'll focus on endothermic first. An endothermic is a process where heat enters a system. So in our case, we're going to always talk about ice being heated on a hot plate. So the hot plate is giving heat to the ice. And what we'll do is, just like the temperature versus time graph, I actually had you guys predict. And most people, including yourselves, decided that, okay, it's going to start down here, and then it's going to slowly increase and increase and increase. But instead of going at a constant here, you guys said it just kept on increasing, which is typical. Most people actually think that occurs, but it really is not. And we're going to see why our actual phase change graph looks like this as opposed to just a constant, and hopefully get into the reason, the real reason why it is, and not just be able to just look at the shape. So the first thing that we're going to do is we're going to focus on A. In A, we have a solid, and there's no phase change occurring here. So just because there's one phase, we just have a solid, so no phase change. At this time, we have our solid block of ice, and we are lower than zero, but we are starting to increase the temperature because we've put it now on the hot plate. So let's just say we got this ice from a deep freezer, which is below zero, and we put it on the hot plate. So at that time, when we put on the hot plate, it does start to increase temperature. During that time, the molecules will start slow. So they are moving, but they're moving extremely slow, and they're speeding up as we increase the temperature. Now, if you look at the bottom, you're going to see that these guys have high attractive forces. So if you look at a solid here, solids are solids because they have attractive forces and they're high attraction. That's why solids keep their shape, because the molecules have this kind of like, it's not a bond because it's a physical presence, it's a physical force, but it's kind of like holding hands. So solids, just like you would be on a cold day, like if we had a fire drill, you and your friends and you had no coats, you guys would go outside and you would like clump together, right? That's what solids do. They clump together and they actually kind of hold hands. They have this physical attraction between them. We call that attractive force. And they have high attractive forces, which keeps their shape. Okay, and we're going to see what happens to that attractive force as we go through. So that's section A. Now, once we get to a point where we call it the melting point, we start seeing liquid forming. So what happens here, this is when we see a constant. The temperature remains constant. So right when we see liquid or solid turning into a liquid, we now have no temperature change. And we're going to take a look at that. So at this time, we have the solid going into the liquid. So you see just even a little bit of liquid. We call that melting. The speed now is constant, like we saw in the graph, and we have a temperature that is constant as well. You're going to see that we completely interchange these two, speed and temperature, because if speed changes, so does temperature. And that is a direct relationship there. And water would be 0 degrees Celsius at this point. So anything with water, when we see melting, it's 0. Now, the weird thing is, let's just say I had a cooler cup, like a Yeti or something like that, full of ice water. And then I had a Yeti cooler, like a big cooler full of ice water as well, like 50 ice cubes in the cooler with water and 5 ice cubes in the cup with water. Now, as long as they're both in thermal equilibrium, they're actually both the same temperature. They're both at 0 degrees Celsius because they have two phases present. The speed is going to be the same. The temperature is going to be the same. While that seems really weird, as long as it's melting, meaning you have ice and water together, it's going to be 0. It doesn't matter how much ice you have or how much water you have, as long as it's both in there and it's in thermal equilibrium, it's going to be 0. So that's pretty weird. And now we're starting to see when we look at these attractive forces. So right here, this is your solid. Again, high attractive forces, but here, the yellow and here is where these start turning into liquids. And these guys have low attractive forces. So we're not increasing the temperature here. If the hot plate's not increasing the temperature, what the hot plate is doing is actually breaking up these attractive forces. Okay, so that's kind of the big idea here is what we're looking at. So let's take a look at section C and see what happens here. So at this point, everything is turned to a liquid. So we have everything melted. It's now liquid. And now we can start speeding it up again. This is why you see a temperature increase. So it goes from 0, or I guess 1 or something above 0, all the way to like 99.9. And now that these are all liquid, we now have all low attractive forces. So there are no two phases. And because we have all low attractive forces, we can now speed all that stuff up. And that's why we're going to have an increase in temperature there. Again, that direct relationship. All right, and then once we get to this temperature, that would be a special temperature for water, which would be 0 degrees Celsius, we now have another constant. What's happening here is it's starting to boil. So we have a liquid turning into a gas like we see in this picture. So we call this vaporization. And at this point, once again, we're seeing the constant speed here. So no longer is the heat from the hot plate going into increasing the speed. The speed stays the same. So does a water temperature. So if this water was boiling for a minute, it would be 100 degrees. If this water is boiling for 20 minutes, it's 100 degrees. If it's boiling for 2 hours, as long as you see both phases present, it's 100 degrees. So again, where is the temperature going? Well, here we see is this would be liquid water, the little attractive force down here in pink, and then right here in green, we have no attractive forces. This is the gas. So what's happening is all of the energy is going into breaking up these attractive forces and turning it into gas. So it's not changing the temperature or speed, it's changing the attractive forces. So that's where the heat is going. And we'll take a look again here at the next one. So once we then get to E, and we have all gas, we now have 0 attractive forces. So when we have 0 attractive forces and it's all the same phase, we can now speed it up. It's going to continue to get faster and faster, which is going to increase the temperature. So what we're seeing here is when we only see one phase present, the temperature actually does increase because the molecules are speeding up. Now, if we see two phases, there is no temperature increase because the molecules are speeding up. And the reason why, because all of that energy from the hot plate's actually going into breaking up those attractive forces, and it can't go into speeding it up until all of those are all one phase. So if we take a look here, this is just kind of a quick overview of all of the different types of matter, including some that you don't need to know. Sorry. So the first state of matter that they're going to go through, so we obviously know about what is matter. Anything that has mass and has volume, which takes up space. The first step of matter, that's the lowest temperature, would be right over here. The highest temperature would be plasma. Both of those we don't focus on. It would be things that would be upper level chemistry, even more like AP chemistry, not even your chemistry you'll take in your typical high school class. So they'll go through it. So for those of you who have not heard anything about that, but this is where this is kind of like it would be at absolute zero, where you have no kinetic energy. That's the only time the particles aren't moving. Now these are where we actually start to look at. So we have solids, and take a look at the different energy type together, they vibrate. Okay, so they are moving. This is, again, they have really high attractive forces, which means they have a definite shape and volume. Because they can hold their shape, it's because they're attractive forces. Now the next one is liquid. So less attractive forces because it has more energy, and the attractive forces is harder to hold on to. They can move and they can move freely, but they do have a definite volume because they can fill the shape of the container. And then the last one we focus on is gas. So if we have gas, it definitely has zero attractive forces, which allows it to move freely and take up more space because it has such high kinetic energy, meaning the energy or the motion is so fast. Now, you can get into plasma, but pretty much plasma is just a highly charged gas. So if we take gas and then we increase the temperature and have electrons spinning around in them, then that's what we're going to have, is plasma. Okay, so now I think we get the point of that. Let's take a look at let's take a look at our next kind of set of slides. So now we're going to go backwards, and we're actually going to look at exothermic. So we've gone through endothermic, we've looked at heat entering the system. Now if we look at exothermic, this is when heat exits the system. So this would be anything that we would be doing with cooling. So if we had a gas per se and we put it into a freezer, this is what we would see here. So over time, we are decreasing the thermal energy that it consists of. So if we look at F, and I'm going to go through this pretty fast. F is when we just have gas. Again, no phase change because one is present. This is when it starts fast, but it's going to start slowing down because we are taking the heat energy out. Because it's slowing down, we'd see a decrease in temperature. And now, when we see a gas to a liquid, we would see the phase change is condensing. Okay, so we are now creating a liquid from the gas. And at this point, because we see two phases, it's going to be constant. Because what's actually happening here is we're increasing attractive forces. And until all of those attractive forces are then going into the liquid, we won't be able to see any change in temperature. So at this point, the condensing temperature would be 100 degrees. That's the same thing as your boiling temperature. So they're at a constant fast speed, which is going to allow a constant temperature as well. All right, so then we go to H, and since everything is now a liquid, it has low attractive forces, we now can say it can start slowing down and slower and slower. Again, if we put something into a freezer or something like that, because it's slowing down, we would see a decrease in temperature, again, because we only have one phase present. But when we have multiple phases present, like we do in I, when we see the freezing point, this is when we see a liquid turning into a solid. So the exact instant we have something starting to crystallize and turn into a solid, we call that freezing. And at that exact moment, it becomes a constant temperature because all of that energy, lack of energy, is going into creating those attractive forces. And until all those attractive forces are created, we can't decrease the temperature. This is why if you have something that's just starting to be ice and then mostly water but starting to be ice, as opposed to something that's mostly ice but still has a little water, they're exactly the same temperature because all that's happening is just increasing those attractive forces between them. This all happens at zero. So little ice, mostly water, 0. Mostly ice, little water, 0. Might not seem like that, but it definitely is if we take the temperatures. And then once everything is becoming a solid and we have all those attractive forces on there, we can get slower and slower and slower, which means we're going to have that decrease in temperature. So again, if we look at this, and I know I went through exothermic pretty fast, exothermic is just the taking heat out of the system. So we would have some sort of gas and we would cool it down by putting it into a freezer or some other cooling contraption of that sort. All right, so now kind of some important information. So one thing we've talked about is the relationship between temperature and a thermometer, or sorry, temperature and speed. Now, temperature is just a measure of the speed of the particles. So we can't actually physically see the particles moving in water. But the cool thing is if we have a thermometer, we can measure the speed of those particles, because the thermometer is kind of like the speedometer of the particles. Just like a speedometer in your car, the speedometer in your car tells you how fast or how slow you're going, or if you're going at a constant. So if the speedometer in your car reads 65 miles per hour and you're at a constant, you're not moving. You're not changing your rate. It's just staying the same. You're staying at a constant speed. Well, same thing here. If we start at, or if we're at 100 degrees Celsius, we are staying at that constant speed, and the thermometer allows us to see that. So again, think about a thermometer as your speedometer for your molecules there. And then this is the big idea. Particles do not change their speed or temperature during a phase change because all the energy is going into overcoming the attractive forces between the molecules. So if we're talking about an endothermic process, we can see here that the solid has all of these kind of like dots here, and those are attractive forces. Those aren't like the compounds themselves are staying together, but the forces between them are really, really strong in a solid. And what happens is when we start melting the solid, these attractive forces one by one will disconnect. And when they start disconnecting or weakening, then they start becoming into a liquid. But it isn't until all of these have weakened and it becomes into a liquid that we can start speeding those molecules up. So all of the attractive forces have to be weakened in order to be a liquid, all of it a liquid, and then increasing the temperature. And then the same thing with this. When we go from a liquid to a gas, once some of these become a gas, we stay at that constant, and all that heat goes into then breaking off the rest of the attractive forces. And then once all the attractive forces here are gone, then we're left with all a gas. And then once we're all one phase, again, we can start increasing the temperature. So the big thing is, if we have two phases present, the energy is not going into speeding up or changing the temperature. It's going into changing the attractive forces. Once all the attractive forces are changed, then we can then increase or decrease the speed, which will then increase or decrease the temperature. So where is the energy going? Into the attractive forces. We can't see that, but we're going to demo that during our lesson. So if you still have questions, hold on to the lesson or ask. It doesn't matter. But if after the lesson you're still really confused, please ask. This is definitely a very abstract and hard concept because you can't see any of this stuff, and it's not what you expect. So please let me know if you have questions, and we'll see each other in the lesson.